Okay, we are studying the system of particles, and today we consider scattering. In the previous class, we studied the two-body interaction under a central force governed by the inverse square law. In that case, we found that the energy, both the total mechanical energy and orbital angular momentum, are conserved quantity. In case of our potential energy is minus k over r, that means 1 over r squared force, then the minimum value for the radius can be obtained by putting the time derivative of a radial velocity. Here u was introduced. U was 1 over r. When r goes to minimum, u goes to maximum. If the particles are trapped in a bound state, then we have r max and r minimum. If it is not trapped, for example, it is a hyperbolic or parabolic orbit, then the u max, the r max goes to infinity and the u min goes to 0. In any case, that those extreme values can be obtained by solving the quadratic equation of r or u. Because r dot equals 0, radial kinetic energy vanishes and total mechanical energy gives a quadratic equation. If we reorganize this equation, it becomes a simple form, and we have the definition of alpha, that is a semi-lattice rectum, and that is orbital angular momentum squared over mu k. Thus, we can replace this one with 1 over alpha and minus 2 mu e over L squared. The solution to this quadratic equation is 1 over alpha plus minus a square root 1 over alpha plus this value. As we can see, because there is 1 over alpha squared, we can factor this 1 over alpha out. We find that it is 1 plus something and 1 minus something. And 1 plus something is a maximum value. We should be careful in case this is a positive value. If it is positive, then this square root is greater than 1. Therefore, it can be negative if I put the negative sign on it. So that is unphysical value. So that this one cannot reach that value, right? So there is a restriction of the angle, polar angle, for the orbital motion. Anyway, u max or r minimum can always obtained by using this positive sign on it. Here, this one is actually the eccentricity of the orbit. From this expression, we find u equals 1 over r mu k over L squared, that is related to alpha, and expressed as this is extreme value. So it is reparameterized by the cosine theta minus theta 0. We can put theta equals 0, then it is 1 plus epsilon cosine theta 4. So that is the maximum value of the u, and that is the reciprocal of this is the minimum value of the radius r. Therefore, this is the eccentricity, and this is the semi-lattice rectum. And all these geometrical parameters are completely determined by strength K and the total mechanical energy E and orbital angular momentum L. Let's further look into the polar expression for the orbit. These are all the conic section, and this is a cone. If I cut it in the horizontal way, we obtain circle, and if it is slanted, it becomes ellipse. And if the angle is parallel to this side, then what we obtain is parabola. And then if the cutting plane is steeper than that for the parabola, then we obtain the hyperbola. If we set theta equals 0, that the polar equation becomes alpha over r plus 1 plus epsilon cosine theta. Here we remember this is the orbital angle of the theta. We began with the 2D polar coordinate system, and Lagrangian was written in the relative coordinate, r, that is absolute value of the difference in the position, the displacement between the two interacting particles, and angle, it was the orbital angle. The trajectory is the conic section of in this form, and alpha is called the semi-latus rectum, and epsilon is eccentricity. If we reconsider the total mechanical energy expressed in terms of the radial kinetic energy and the rotational kinetic energy, that involves the orbital angular moment. In the sense of one-dimensional motion along the radial direction, these two contributions can be understood as effective potential energy. And if we consider these two as effective potential energy, it is explicitly written in the form as long as the potential energy is follows the inverse square law. The derivative, and put negative sign on it, we can obtain the effective force. And effective force is the actual radial force and the centrifugal force. If K is a positive, it is attractive interaction. K is a negative, then repulsive interaction. We first consider the simplest case, the parabolic case. Parabola has the semi-latus rectum and the eccentricity and formula. All these formulas are the same for everything, except that the eccentricity varies depending on the situation. And eccentricity becomes 1 in the case of parabolic form. Parabolic form has the energy equals E equals to 0. So that it is just like closely related to escape velocity of the orbit. Okay. Write down the Hamiltonian effective force, effective potential energy, and effective force is can be computed. If total mechanical energy is equals 0, as r goes to infinity, potential energy becomes 0. That means as r goes to infinity, the kinetic energy of the particle must be 0. That means this radial kinetic energy vanishes as r goes to infinity because E is 0. E is 0, then epsilon becomes exactly 1. No, E is 0. Eccentricity is exactly 1. Therefore, it is 1 plus cosine theta. So alpha over r equals 1 plus cosine theta. We expect that alpha equals 1 plus cosine theta, alpha, and the minimum value of r is alpha over 2, right? 1/2 of alpha, when theta equals 0. When theta equals plus minus pi, it becomes -1, so denominator becomes 0, and r goes to infinity. So the parabolic curve comes from the infinity and to the infinity. And this is the minimum value. Minimum value r, because of this, r min equals half of alpha. Okay? And we remember the focus, the distance from the focus to the particle on this orbit is defined by r. It is not the radius from the center. That is usually, if we use this kind of parametrization, y squared minus 4cx, in that case, the focus is outside and origin is at the vertex. But in our case, the conic section formula is formulated when the focus is placed at the origin. That's quite important. Focus is placed at the origin when we write down this conic section formula. All right. So the focus is placed as a fixed, and this is the relative distance between the two interacting particles. All right. So alpha is the semi-lattice rectum. That is the straight line that is perpendicular to the symmetry axis. The length of the straight line passing through the focus is called the lattice rectum. And the half of this is called the semi-lattice rectum. So this chord, half of this chord is called alpha. And eccentricity equals 1 means eccentricity is actually this distance divided by this distance. That means that this is the directrix. Point P of r theta, this is r and this is theta, angle between the symmetry axis and the straight line connecting the focus and the point. This is theta. Okay. The distance between the directrix and the focus are the same. This is r, this is r. Okay? Therefore, this distance same, then we have this kind of equation. When the origin is at the vertex, this is vertex, focus. All right. If I draw a straight line along the symmetry axis, the distance between these two is the same. If I put a straight line, this is a semi-lattice rectum, and this distance should be the same as this distance to the directrix. Therefore, this is alpha and this is alpha. Okay? The distance between focus and directrix is alpha in the case of parabolic orbit. In addition, this vertex is in the middle of focus and directrix. So the vertex is placed at the center of this alpha. Therefore, this distance is a half of semi-lattice rectum. That's the reason why we have obtained R minimum. This is the R minimum. It is approaching and becomes minimum and goes far away. This is the R minimum is a half of semi-lattice rectum. Let us consider further. This is conic section directrix. This is lattice rectum. This is semi-lattice rectum. Semi-lattice rectum is alpha. And we remember alpha is orbital angular momentum squared over reduced mass times strength K. Okay. In general, the distance ratio of the semi-lattice rectum to P R over this one is to be defined to be eccentricity. And eccentricity in here is just 1, so energy equals 0. Okay, this is the ratio, and we put epsilon equals 1 here. The radial equation, the polar equation becomes this one. Next, we consider elliptic motion. Ellipse can be defined in 2 ways. Just to put 2 foci, this foci of one focus and left focus, trajectory of a point whose distance to the f and f prime, 2 foci, becomes this, a constant. And we say this distance, this is the major axis. And this is a semi-major axis. This is minor axis. And this is a semi-minor axis. Okay? Major axis, this is semi-major axis, A, and focus is defined by epsilon times A. And because this is ellipse, this focus is inside ellipse, so epsilon is less than 1 and greater than 0. Okay. When epsilon becomes 0, these foci combines. They collapse to a single point and it becomes a circle. If the sum of 2 distances are 2a, then we find that if this point comes here on the x-axis, the distance from here to there is this, and this distance, this is doubled, and this part can be moved to here to make 2a. Alright, the sum of the 2 distances are the sum of this string, the length of this string is 2a. When this point is on the y-axis, it becomes symmetric, and the sum of this string, this length of this string should be 2a, so this side, the hypotenuse, becomes a, and this is a. Because this is semi-minor axis b, and this is a focus, so that is epsilon a. So we have a right triangle. We find that a squared equals b squared plus f squared. All right? And substituting epsilon a to a focus, we find the b squared is a squared times 1 minus epsilon squared. From here, b is a times the square root of 1 minus epsilon squared. Eccentricity can be expressed in terms of the focus divided by the semi-major axis. Again, it should be the same as the ratio of the point to focus to point to directrix. Okay? All right. So directrix, this focus to this point, this one is a 1 minus epsilon, right? And this point to there, this is PD. So right now, this length should be greater than this one by 1 over epsilon. Something like that, right? This length, this one divided by this one should be epsilon. right? All right. So eccentricity can also be expressed as semilatus rectum. Semilatus rectum can be obtained. This is semilatus rectum, right? So formula is formula for this ellipse with the origin is at the center, that is this. So the coordinates of this point is f, x-axis f, x value is x component epsilon a, and y component is a semilatus rectum. Substitute these two values in here, and we find that alpha is semilatus rectum is expressed in terms of a multiplied by 1 minus epsilon squared. A 1 minus epsilon squared, we find this one and this one, b squared over a equals a 1 minus epsilon squared, right? If we use this one, this is a, and a, this length is a, and this length is 1 minus epsilon. If we combine, this is epsilon over a, all right? This is a. If I sum 1 minus epsilon plus epsilon, a over epsilon. Wait a second. Just ignore this. Okay. So semilatus rectum is alpha, and that is a 1 minus epsilon squared, or b squared over a. We continue to consider the eccentricity of the ellipse. And as I told you, the point to focus divided by point to directrix. That was we obtained wait a second. Focus divided by a, that is epsilon, and this ratio, right? All right. So this is wrong. Here I missed the factor of epsilon, because this to this should be epsilon. Epsilon must appear here. Okay. All right. That means position of the directrix is this one. So alpha over epsilon. All right. So that is right. B squared over epsilon A. Alpha over epsilon. Everything is right. Okay. Therefore, using this relation, the ratio, this ratio, F to A, that is epsilon, and that is PF divided by PD. And the parametric equation can be found if by taking the ratio of PF and PD. We square this equation to find the quadratic form, and after cancellation we find 1 minus epsilon squared x squared plus y squared is this form. We divide both sides by a squared 1 minus epsilon squared, then we find that this expression here, b squared is a squared 1 minus epsilon squared. So elliptic form is completely open. Next, we consider the polar coordinate equation for an ellipse. First, this parametrization is at the origin. This origin is placed at the center. But what we are interested in is to put the origin, match it with this focus. That means move this, keeping the axis the same, move this ellipse to the left by this amount, because I want to put the origin to be placed at the focus. And the radius becomes, this is the radius and this is the angle theta. Alright, in that case what I need to do is substitute, figure the graph fxy equals 0 can be translated by this if we substitute x with x plus epsilon a. So substitute x plus epsilon a into x and square. Expanding all of the expressions, you can follow this detailed calculation. At the end of the day, you will find x squared plus y squared. This focus is there, r is here, polar angle theta is here, and x squared plus y squared is the radius, right? And this one is factorized. Combining these two pieces, you have the completing, we can complete the square. The absolute value of both sides gives the radius on the left hand side. Right hand side we have this one, a 1 minus epsilon squared, that is semi-latus rectum, that is alpha. And because alpha is greater than ER cosine theta, so this one should be put on the left, alpha minus epsilon r cosine theta. Reorganizing the expression by migrating to the left hand side, we have r 1 plus epsilon cosine theta equals alpha. So r equals alpha over epsilon cosine theta for elliptic motion. This is epsilon between this. And in case epsilon equals 0, it is just a circle. The Kepler's law, the second law, or the first law, states that it is the orbit is an ellipse, but in the case of epsilon becomes 1, it should be parabola. And when epsilon becomes positive and greater than 1, in that case this one becomes hyperbola. Let us consider the eccentricity of the ellipse. Ellipse, in all cases of conic section, eccentricity is square root 1 plus the 2e L square over mu k square. And we remember this energy is total energy is negative in order to have a bound state. The parametric equation shows that R equals alpha over 1 plus epsilon cosine theta, and elliptic orbit epsilon is between 0 and 1. And 0 is allowed for the circle. If I vary the angle, it ranges, cosine becomes, runs from -1 to +1. Therefore, maximum value of radius is obtained when it becomes -1. Minimum value of the radius is obtained when it becomes +1. Because alpha is a times 1 minus epsilon squared, if I substitute here, R max is a 1 plus epsilon, and R minimum is a 1 minus epsilon. Using these expressions, the product of R max and R min for the elliptic orbit product is a squared 1 minus epsilon squared. A squared 1 minus epsilon squared. That is b squared. Sum of these two, an average, arithmetic average of this R max and R min, that is A. 1 over R, 1 over R. 1 over R max plus 1 over R min. It becomes, product is here, B squared. Sum is 2A, this one. Equipped with these formulas, we can attack the Kepler's second law and third law. Kepler's second law is the area velocity. Area velocity is the actually time rate of spanning the sector. That is 1/2 r squared theta dot. Because the area of a sector is 1/2 r squared d theta. And if I take the time derivative, it becomes 1/2 r squared theta dot. Because the angular momentum is preserved, and orbital angular momentum L equals to mu r squared theta dot. Here, r squared theta dot is L over 2 mu. In addition, the relation for R max and R min for energy, because energy is a conserved quantity, and at R max and R min, the radial velocity disappears. This value is the same for R max and R min. And this one gives the equation, this kind of equation. So this one is a factorized. We have these two factors, so remove this, and we find over factor L squared over 2 mu k. But L squared over mu k is actually the semi-lattice rectum alpha. So alpha over 2, 1/2 alpha. And after erasing this, we have this factor. So this one appears, this factor. After removing that one, we have 1. All right, L squared over 2 mu. L squared over 2 mu. L squared over 2 mu is k over this value. And that value is already obtained. This 2a over b squared. If I substitute 2a over b squared in here, kb squared over 2a is this. Okay? Now, we find L over mu equals 4a over L mu squared. This one. Alright? L over mu. 2 is moved to here. Okay? Multiply. This one is missing. L squared over mu squared equals, so 2 disappears, and wait a second. L squared over 2 mu equals to KB squared 2A, cancel, multiply mu in the denominator. Okay? Next, we have period. Period is the area of an ellipse, that is pi AB, divided by the area velocity. Area velocity is written here, so L is here, pi AB is here, 2 mu appears here. Let us square this formula, square t squared, 2 pi AB squared, and mu over L squared. Mu over L squared. So mu over L squared, according to this formula, mu over L squared is A mu over KB squared. So A mu over KB squared. So t squared is 4 pi squared A squared A cube, B squared cancel, and K in the denominator, mu in the numerator. Kepler's third law, there's a harmonic law, states that the period of elliptic orbit squared is proportional to the cube of the semi-major axis. Next, we consider the energy. If I consider the energy, this is the energy, they are the same. After substituting the previous result, the sum of these two is 2 times the energy. And we have these relations, substitute these relations into the sum of these two energies, we find that this is expressed in terms of minus 1 over A equals 2E over K. From this, total mechanical energy of the system is minus K over 2A. It is not R, but A. 2 times semi-major axis. So the energy is minus K over major axis. Okay. Next, we consider hyperbolic orbit. Hyperbolic orbit is obtained by cutting the cone the vertical way, at least steeper than this angle. Then in any case, we will find the hyperbolic orbit on this plane, conic section. The elementary definition of the hyperbolic orbit is the distance from the two foci to a trajectory has equal difference. Here, for example, this point, this distance subtracted by this amount, this is the same as this, then they are cut, and this is 2A. So distance difference becomes 2a, that is hyperbolic orbit. Substituting the expression for the coordinates, when we put the origin to be the central point, then after the calculation we find that the equation is x squared over a squared minus y squared over b squared. Here, focus is placed in an epsilon a. Epsilon a. Alright. What happens to the semi-lattice rectum of a hyperbola? Alpha is very important to determine the radius, the minimum value of the radius especially. This is semi-lattice rectum, and according to this formula and focus coordinate, f alpha is substituted to find alpha. F alpha is substituted. Then the result is alpha is a epsilon squared minus 1. That is b squared over a. This one is always the same. But the position of directrix is different depending on the geometric object. Eccentricity expression can be pulled out from this formula. This is moved, it is a b squared over a squared. 1 is moved, that is 1 plus b squared over a squared. And we have taken the square root to find epsilon. It is manifest that epsilon is positive and greater than 1. Because epsilon is greater than 1, the distance to the focus is longer than the distance to the directrix, and the directrix is placed in here inside. Let us look at the directrix and eccentricity of the hyperbola. The distance ratio, this distance divided by this one divided by this one, should be the directrix. This is directrix, and directrix coordinate is a squared over f. That is. So if we make use of this expression, let's see. F equals epsilon a. For example, this distance is a epsilon minus 1, and this distance should be 1 over epsilon minus 1, because this one divided by this one is epsilon. So this distance is like that, and now this is the origin and this is EA. This is epsilon A, right? No, this is not epsilon. All right. And this position, this is A, because if we substitute A0 to this expression, that satisfies. So this distance is A. This is A. This is unknown, X. This is a minus x, right? This is a minus x. A minus x over this distance, a 1 minus epsilon. That should be epsilon. So a minus a epsilon equals a epsilon minus this one, right? All right. There is something wrong. So you can check all these calculations because our time will be up soon. Okay. So anyway, Directrix is this is correct one. So if you follow the calculation, you finally end up with the normal expression for the hyperbolic form. Next, we consider how to derive the polar equation for the hyperbola. This equation is valid when the origin is at this place. But in our case, our focus should be at the origin in order to describe the conic section. We choose the point, this point, to be origin. That means we have moved to the right so that this one matches will move to the right. How much? By focus, epsilon a. So this one is to be moved to origin. So epsilon a is the amount of shift. And that is the coordinate of the focus in the positive sense. If you substitute this f, x minus f in here, this is the expression when this one becomes new origin. And after the calculation, if you follow all these calculations, you find a squared x squared plus y squared. That is a radius squared. And the right side is factorized as in this kind of form. We substitute f to be epsilon a, and we find this kind of expression. Divide both sides with a, then r, epsilon r cosine theta, right? And then b squared over a. That is semi-lattice rectum alpha. Therefore, in this hyperbolic case, we also have exactly the same parametric form, r equals alpha over 1 plus cosine theta, where epsilon is greater than 1. Okay. Next, we consider scattering cross-section. First, we will consider the inverse square law. If we know this, then orbit is determined in this way. Once the orbit is given in this form, the semi-lattice rectum alpha is L squared over mu k. Eccentricity of the orbit is square root 1 plus 2e L squared over mu k squared. Therefore, as long as you know the reduced mass, orbital angular momentum, energy, and the strength of the interaction, then everything is completely determined. If the energy is negative, then the eccentricity is less than 1. And in case epsilon equals 0, it is a circle. And if it is not non-zero, then it is an ellipse. And E equals 0, then epsilon becomes 1. And this is parabolic form. And if epsilon is a positive, then hyperbolic form. Using this information, we'll continue to study the cross-section. Cross-section is related to the scattering. The scattering interaction probability is closely related to scattering, and this is an example. M1, M2 collides, and this is the impact parameter. Impact parameter, okay. If it is not a contact interaction, for example, 1 over r, the inverse square law, the two particles communicate each other well before they actually meet together. Therefore, even though they are not on the line, the interaction happens. So the perpendicular distance of the two lines, first the incident motion, incident velocity, initial velocity of the incident particle has the direction of this, but it does not pass the M2, the target particle. The parallel line that passes through the target M2, then we have two parallel lines. The perpendicular distance between the two parallel lines is defined by the impact parameter. All right. And during the interaction, we can draw a line connecting the two objects. The distance between the two objects is the relative coordinate that we are describing in terms of after subtracting the center of mass, center of momentum. Okay? The relative motion is always described in terms of relative coordinate. It is not the distance from the center of mass, but the distance between the two objects. This is the initial direction, and after the collision, it follows some way. And the angle between the initial direction and the final direction, this is the scattering angle theta. And during this time, the direction of r changes. This angle is called theta. But this is variable theta, and this is a initial final comparison. This is the scattering angle theta. The variable theta can be cut into two pieces when it reaches the r minimum. When it decreases to reach r minimum and increase to infinity. This angle is called thick theta, and this angle is thick theta too. And because they are symmetric, this angle should be the same. And this angle, scattering angle, can be moved in here. This is scattering angle. The 2 thick theta plus, that is orbital angle, from infinity to r minimum. This orbital angle to thick theta is multiplied by 2 equals pi minus theta, or 2 thick theta plus the theta is 180 degrees. Okay. So at the left frame, the orbital angular momentum L is completely determined by momentum multiplied by this impact parameter, R cross P. So impact parameter multiplied by M1 U1. And M1 U1 can be expressed in terms of the incident particles' kinetic energy at the lab frame. That is expressed in such a way. At the CM frame, the same is true, except that we replace M1 by the reduced mass mu. And this explanation is repeatedly given in here. We have considered what the impact parameter is and the importance of the relative coordinate and how to determine the orbital angular momentum of the initial state at the lab frame and at the CM frame. As you remember, as long as the central force is concerned, the orbital angular momentum of the system is completely conserved. And if we want to compute the scattering angle, we have to compute the relation of the angle between the force and radius, something like that. So this is what we already have studied. So let me in the calculation of thick theta, once you obtain the thick theta, you have twice of thick theta, subtract twice of thick theta from pi, then you obtain the orbital angle, the scattering angle theta. In order to obtain this, you need some calculation involving the related to radius and angle. In the hyperbolic case, if we consider this one with epsilon equals hyperbolic case, epsilon is a positive, R minimum is reached when it becomes a maximum, that is alpha over 1 plus epsilon. And this contribution appears here. So you have to take the integrate some component from R goes to infinity to R minimum, something like that. As cosine theta reaches 1 over epsilon minus 1 over epsilon, it becomes 0 and R goes to infinity. Parabolic case, epsilon is 1, R goes to infinity is the case when theta goes to pi or minus pi. And at theta equals 0, our minimum is approached, and that value is 1/2 of semi-lattice rectum. In the case of ellipse, we have ellipse 1 plus epsilon cosine theta. Minimum is alpha over 1 minus epsilon. Maximum is alpha over 1 minus epsilon. Circle, it is always alpha. Okay, we are all equipped with some calculation of the cross-section. Cross-section is related to the interaction of a beam on a cross-sectional area. You throw something into the area, something is hit by this cross-section and scatters. Measuring the area of this, if you can see, then you can measure the cross-section directly. But if you cannot see, for example, it is a very small, very tiny, then you expect, you just let the flow of particles hit in this region and just count the number of particles scattered from this area. This is the indirect way of measuring the cross-section. In order to study this, we need to know this kind of concept, the number density. We are considering the flow of identical particles, uniform identical particles, just like raindrops or something like that. The identical particles are distributed and in the space, and they are all moving with the same velocity. Okay? First of all, at the rest frame of this flow, we define the number density. The number density N is total number of identical particles divided by volume. And if you multiply if they are equally charged, for example, electron, you can multiply electron charge, single electron charge, to the number density to find out the charge density of the flow. If you multiply the electron mass, then you will find the mass density of the volume mass distribution. Next, we consider the intensity. Intensity is actually defined by the number of hits divided by the number of hits per unit volume, a unit cross-sectional area per unit time. And that is, if you multiply velocity, delta x both sides, then cross-sectional area times the delta x, cross-sectional area times delta x, that is a volume. And the numerator is delta x, is divided by delta t, then that is the velocity. Then you end up with the number of particles per volume. This is number of particles per volume is the number density, and this is velocity of each particle. We assume that all of the particles have the common velocity. So number density times velocity is the intensity. If you multiply the unit charge for each particle and unit mass for each particle, you will obtain this intensity is the current density actually. So intensity multiplied, if every particles are of charge q, then this intensity multiplied each particle's charge is the current density. So current density multiplied by the cross-sectional area is the current, you remember. Let us consider your shooting flow of incident particles. The intensity of the incident particles in this collision is number of hits per unit time per unit area. That is the intensity of the incoming flow. Intensity of the incoming particle flow should be prepared uniformly. If it is prepared uniformly, let us consider the cross-sectional area on which the particles are hitting. The uniform cross-sectional area can be divided into two small pieces. That is a differential cross-section with the impact parameter b ranging from b to b plus dB. Then the area of this annular region will be the differential cross-section. That is 2 pi b dB. If you are equipped with the incident intensity of the particles in this cross-sectional area and the number of hits per unit time on that differential cross-section will be I intensity, incident intensity multiplied by the differential cross-section area. If A is a circle, this differential cross-section can be integrated to find out the total cross-section of that cross-sectional area, and you can carry out the integration to find the pi r square will be the total cross-section of the area. All right, then you just put this beam parallel to the point at which a target is placed, and after the interaction with this target, this flow is deflected radially. If you increase In the case we have the repulsive force, it deflects a lot. If it farther, deflects less, something like that. Okay? If it comes closer, deflects more. So anyway, incoming flow is along the azimuthal and along the z direction, longitudinal direction, and outgoing flow of particles radiates radially. Therefore, after passing through this cross-sectional, small cross-sectional area, the final cross-sectional area increases a lot. You have to remember the number of particles. The incident particle is preserved. Then the number of particles coming in should be the same as the number of particles coming out. But you will find that the intensity of the particle in this large area should be decreasing by 1/r squared, because this cross-sectional area is this sigma detector, that is proportional to the radius squared coming from the scattering center. This r squared times d omega, and d omega is the solid angle element. If there is azimuthal symmetry, then you pull out the azimuthal angle, integrate out azimuthal angle, and find the cosine theta. This can be integrated out for -1 to +1. And here, the particle coming into to make a collision should be the same as particle going out. Number of particles should be the intensity of the incoming particles multiplied by the cross-sectional area multiplied by delta t. That should be the same as outgoing intensity, the outside detector area, and time. Time cancels. But if I want to find out the cross-sectional area, I need to divide this factor in both sides. The differential cross-section can be integrated out to find the total cross-section. The total cross-section can be measured indirectly by measuring the outgoing intensity multiplied by the r squared d omega, 2 pi the d omega, divided by the initial intensity of the incident particles. So this is the way how to compute the total cross-section. And there are various formulas you can follow. This is for the general case, and in case there is azimuthal symmetry, as the last step, we consider the actual calculation of the cross-section. First, orbital angle calculation. The central force problem with the potential energy, depending on r as a function of r, we were able to express the angle change by this expression. The time is expressed in terms of r, and r is expressed in terms of theta. So that is all allowed because the angle theta is the cyclic coordinate, and orbital angular momentum is therefore preserved. By making use of this expression, we can compute the orbital angle theta during the interaction. And we are interested in the big theta for from infinity to r minimum, and the same big theta r minimum to infinity. We can compute this single one and multiply 2, and after that we have scattering angle theta. There is a thick theta, so scattering angle theta should be obtained from pi minus 2 thick theta, right? Initial condition. This is at the CM frame. The total mechanical energy is just the energy of the relative motion, because 1/2 mass is a reduced mass. Two-body system is always described by reduced mass at the center of mass frame, and the relative momentum. This is R dot, right? R is the absolute value. And this one can be computed in this way. You can follow this without any problem. And PR and L, this is conjugate momentum, associated with the coordinate R and orbital angular momentum. Once you know that, you can make use of the fact here, this expression gives 2 mu E equals L squared over B squared. So 2 mu E, this is L squared over B squared. Alright? And in case we have a inverse scale law, then we can substitute the U with this expression. Alright, we can pull this L over B out and replace the integration in terms of T. T is B over R. Then this complicated form is relatively simpler. So this one is very closely related to the arc sine integration. Okay. Elastic scattering from a hard sphere can be computed in such a way. The thick theta can be computed using symmetry of the reflection. For the elastic scattering, the incident angle and the reflected angle should be the same. And once you know the thick theta, if you know the thick theta, then you can replace the thick theta in terms of the scattering angle theta, and find relation between express the impact parameter in terms of the scattering angle theta, and find out the derivative to substitute to this expression to find a differential cross-section. And once differential cross-section is obtained, you can integrate over the solid angle to verify this cross-sectional area is equivalent to that you have expected. And the same calculation can be made using more formal way by making use of the expression integral form of computing the thick theta that we just have developed, and by making use of the fact the potential energy is 0 outside the sphere and inside it becomes infinity, you can evaluate this integral very easily. And at the final stage, you obtained the same expression that can be obtained by simply considering the geometric structure of this problem. Therefore, as a summary, we have completed the study of the system of particles for computing the motion of the two-body system, and especially for the central force problem. And we have verified all of the Kepler's laws, and we have verified the orbit of the central force two-body interaction. It is satisfying the inverse square law. They are satisfying the conic section. That's it.